Hello, Matt here from chemistrystudent.com. In this video, we're going to look at the acid dissociation constant, Ka. We're going to talk about what an acid dissociation constant is, how to calculate acid dissociation constants, and how to use their values to find concentration of H+ ions in a solution of a weak acid. The Bronsted-Lowry theory of acids and bases and the pH scale have been covered in separate videos. Check the links in the description below. Before we talk in detail about acid dissociation constants, there are a couple of ideas you need to be comfortable with. According to the Bronsted-Lowry definition, acids are proton, H+ ion, donors, and bases are proton, H+ ion, acceptors. When added to water, acids dissociate and split apart into H+ ions and their conjugate base. Strong acids fully dissociate when added to water. Weak acids partially dissociate when added to water, forming a solution that contains a mixture of molecules of acid, H+ ions, and conjugate base ions. A dynamic equilibrium refers to a reversible reaction in a closed system in which the rates of the forward and reverse reactions are the same. This means at equilibrium, there is a mixture that contains both reactants and products, and their concentrations remain constant as long as the system remains at equilibrium. A position of equilibrium refers to how the concentrations of reactants and products in the mixture compare to each other. A position that lies to the right means a higher concentration of products in the equilibrium mixture compared to reactants. And a position that lies to the left means a higher concentration of reactants in the mixture compared to products for the forward reaction. Equilibrium constants can be used to show this relationship between reactants and products in an equilibrium system. A value is calculated based on the concentration of products and how they compare to the concentration of reactants in the mixture. Recap done? Let's go. When a weak acid is added to water, its dissociation is a reversible process. This means that as acid molecules dissociate and split apart into H+ ions and conjugate base ions, H+ ions and conjugate base ions can also join back together again to reform molecules of the weak acid. This means an equilibrium can be established between the acid molecules, Ha, H+ ions, and conjugate base ions, A-. The position of this equilibrium is based on the strength of the acid. The stronger the acid, the more dissociation that happens, and the more the position of equilibrium lies to the right. This results in fewer acid molecules in the solution and more H+ ions and conjugate base ions. The weaker the acid, however, the more the position of equilibrium lies to the left, and the more acid molecules there are compared to conjugate base ions and H+ ions in the solution. As a position of an equilibrium system is basically just a comparison of the amounts of product compared to reactants for the forward reaction, we can show it numerically using equilibrium constants. The equilibrium constant for the dissociation of a weak acid can be found by multiplying the equilibrium concentration of hydrogen ions and conjugate base ions together and dividing them by the concentration of acid molecules. This is because the products of the forward reaction are H+ and A-, and the reactant of the forward reaction is Ha. When writing concentrations in formulas, we use square brackets, meaning H+ in square brackets means concentration of H+ ions. The value obtained is referred to as an acid dissociation constant and is represented by Ka. K meaning equilibrium constant and the little a acid dissociation. As positions of equilibrium change with temperature, the Ka value of an acid is only relevant for a specific temperature. The same acid will have different Ka values at different temperatures. Ka changes with temperature. The larger the value of Ka of an acid, the stronger it is. The lower the value for Ka, the weaker it is. For example, at 298 Kelvin, ethanoic acid has a Ka value of 1.74 times 10 to the minus 5. and benzoic acid has a Ka value of 1.6 times 10 to the minus 10. From this, it can be clearly seen that the Ka value for benzoic acid is much smaller than that of ethanoic acid, meaning it is a weaker acid. If you took 1 mole's worth of each acid and placed them into the same volume of water, more ethanoic acid molecules would dissociate than benzoic acid molecules, giving a higher concentration of H+ ions. The value for benzoic acid is very small here, telling us that most benzoic acid molecules don't dissociate. As a result, in a solution of benzoic acid, the concentration of H+ ions and its conjugate base, benzoate ions, would be very low. It is worth pointing out here that strong acids do also have Ka values, it's just the values are very high, meaning a position of equilibrium lies to the right so much that effectively no backward reaction really occurs, and virtually all the acid molecules dissociate when added to water. For example, the Ka value for hydrochloric acid is 1.3 times 10 to the power 6. That is a very big number and is over 100 billion times larger than the Ka value for ethanoic acid. This tells us the position of equilibrium lies massively to the right, making it a strong acid and telling us that minimal reverse reaction is occurring. As Ka values can be very small for weak acids, pKa is sometimes used to make the values easier to work with. pKa refers to the use of a logarithm of Ka to the base 10. Logarithms and their use have been covered in a separate video about the pH scale. Check the links in the description below. In short, the pKa value of an acid equals minus log to the base 10 Ka. And this means Ka of an acid equals 10 to the power minus pKa. For example, the value for Ka of ethanoic acid at 298 Kelvin we've already seen is 1.74 times 10 to the minus 5. Its pKa would therefore be minus log to the base 10 times 1.74 times 10 to the minus 5, giving 4.76. This is a much nicer number to work with than 1.74 times 10 to the minus 5. If the concentration of a weak acid solution is known, we can use its Ka value to determine the pH of the solution. By rearranging the expression, Ka equals concentration of H+ times by concentration of A- divided by concentration of weak acid, Ha. As a weak acid molecule Ha dissociates, it will release a H+ ion and an A- ion, its conjugate base. For every 1 mole of Ha that dissociates, 1 mole of H+ and 1 mole of A- will be released into the solution. The moles of H+ ions produced from the dissociation will be the same as the moles of A- produced. This means the values for H+ concentration and A- concentration in the Ka expression become the same, meaning when multiplied together they give the same value as H+ concentration squared. We can now substitute H+ concentration squared into the expression instead of H+ and A- concentration. Now Ka equals H+ concentration squared divided by Ha concentration. A bit of rearranging gives us Ka multiplied by Ha concentration equals H+ concentration squared. This can be simplified down to H+ concentration equals the square root of Ka multiplied by Ha concentration. For that last step, we just took square roots of both sides of the equation to turn H+ concentration squared into just H+ concentration. By using the value of Ka for the weak acid and its initial concentration, we can find H+ concentration. This could then be used to find pH, as outlined in a separate video about pH. Check the links in the description below. One thing to point out here that you may already have noticed is that we have used the initial concentration of weak acid in the Ka calculation, when actually it should be the concentration of weak acid at equilibrium. The point being here that as the acid dissociates, its concentration will decrease slightly, and therefore the initial concentration won't be exactly the same as the concentration at equilibrium. The reality is that the amount of dissociation is very small, and as a result, we ignore this problem and simply assume the equilibrium concentration of weak acid to be the same as the initial concentration. Mathematically, it makes very little difference, but you should be aware and understand that we are making this assumption when we carry out such calculations. So, to summarize, weak acids form an equilibrium system when they dissolve in water. The equilibrium is between weak acid molecules, Ha, their conjugate base ions, A-, and H+ ions. Acid dissociation constants, Ka, are equilibrium constants that describe the position of equilibrium for the dissociation of a weak acid at a particular temperature. They are based on the concentration of weak acid, H+ ions, and conjugate base ions at equilibrium, and are found using the expression Ka equals H+ concentration times A- concentration divided by Ha concentration. The larger the value of Ka, the stronger the acid, as this means more of it has dissociated in solution. To make representing larger and smaller values easier, pKa is sometimes used instead of Ka. pKa equals minus log to the base 10 Ka, and Ka equals 10 to the power minus pKa. Ka values can be used to find the concentration of H+ ions in a solution formed by a weak acid. We assume minimal dissociation of the acid, meaning initial concentration is used as equilibrium concentration in the expression for Ka. And as H+ ion concentration will be the same as A- concentration at equilibrium, Ka equals concentration of H+ squared divided by the concentration of Ha. I hope you found this video useful. Please check out other relevant videos in the links given in the description below and visit chemistrystudent.com for free notes and revision materials.